pleased to introduce Professor Hartmut Führ from Aachen University from Germany. His topic about coarse geometric methods for generalized wavelet approximation theory. So Professor, Zoom stage is yours.
Thank you very much for the introduction, and also thank you very much to the organizers for this, for the invitation to this very nice conference. The title is maybe a little imprecise because this is essentially one criterion which uses coarse geometry for one particular purpose. I believe there's probably more to do in that domain, but we'll talk about that later. So let me give you a short overview of the talk. Essentially, first I will try to, as usual, try to explain the words in the title, and I will talk about a very general class of wavelet systems. The definition is probably slightly unusual or in its generality, but you'll see about that in a minute. And then I will talk about the spaces that these systems define in terms of decay properties. Those are essentially the spaces of well-approximated functions by those systems. And the question that we want to ask is, given two different types of wavelet systems, can we decide whether they have the same approximation theory? And the answer to that is going to involve a quasi-isometry property of a certain map. So that's where the coarse geometry comes into the game. In the end, I want to present two little applications of this general principle. Okay, so that's the general outline. Let me start first by what I understand by generalized wavelet systems. It's really just a family of convolutions. So we start out with essentially some family of functions in L2RD. Later on, they will actually have to fulfill more properties than we would put on the slides. A general warning, this talk is not, I've decided to skip a lot of technicalities, so there's always some sort of mental footnote attached to at least most of the results that I present here. But in essence, they are rigorous and complete. But anyway, so we start out by a family of functions in L2 that we want to, which we call reproducing, essentially if convolution by that family captures L2 norm. So by that I mean, if you take an arbitrary L2 function, convolve it with all the elements in the system, what you get, and you then sum up the L2 norm squared, you get back the L2 norm squared of the function you put in. And if you use a little Fourier analysis, it's well known that this essentially boils down to a partition of unity property that the Fourier transforms have to fulfill. Essentially, that the Fourier transforms squared have to sum up to one of those of the generalized wavelet system. And another fairly general observation is that in such circumstances, you can always retrieve your function f by just convolving with Cj and then with Cj star, and then summing up. And what you get is something that converges unconditionally in the L2 norm. Yes, and so here I will, throughout the talk, I will stick to mostly countable systems of such generalized wavelet systems, but there's also going to be a lot of examples that arise from continuously indexed systems. I comment on that later on. Okay, that's just the general definition. And now just a couple of examples that shows you that there's a wide variety of constructions to choose from. All of these have their own communities in some sense, and all of these have been studied for a while. So that those are the initial ones. You essentially take a single function psi, suitably chosen, and then you take you dilate this function by powers of 2. And yes, and if you do it properly, then what you end up with in the end is actually, I think here you probably have to need to, no, I think this is correct. If you want to want this to add up to fulfill the Calderon condition from the previous slide. I think this is the correct normalization. Okay, then Gabor systems, essentially, again, you can, it's a countable system indexed by the integers, but this time you're not using dilation, you're using modulation or frequency shifts. Then other examples in dimension 1 are so-called ERB-lets. Those are systems of filters in one dimension that are somewhat designed to mirror the acoustic system. Then there are multi-window Gabor systems and well, a couple of other constructions that I now can't put my finger on. Those are all examples in dimension 1. In dimension 2, one of the things you can do is you can look at oriented wavelets where you essentially pick a single function, also dilated by powers of 2, but then also rotate by a discrete set of rotations. You can use that. Again, you can use Gabor systems in dimension 2. Then another construction in dimension 2 are so-called shearlets. So here I'm using a discrete family of shearlets. So those are essentially, again, obtained by picking a single function and acting on it by a family of matrices. And the matrices combine shearing and anisotropic dilation. And then there are other related constructions, so-called curvelets, which were actually invented prior to shearlets, cone-adapted shearlets, and you can play this game in dimensions higher than 2 and with other groups. Okay, but I will comment on shearlets at the end of the talk in more detail. Another thing, another game you can play in another type of construction of such systems that you can look at are anisotropic wavelet systems, where you start out with a matrix that's expanding, which means that all eigenvalues have modulus greater than 1. And essentially, again, you take a single function and you take dilates, but this time by the powers of your expanding matrix. So essentially, think of something like the diagonal matrix with entries 2 and 4. So as the power j grows, the matrix is dilating more in the first direction than in the second. So the scaling becomes more and more anisotropic. Yes, and then this is the homogeneous anisotropic wavelet system that you get if you take integer powers for arbitrary j and z. That's what's missing here. So here I'm for the homogeneous system, I'm taking j from all the integers, and I'm just taking j from the positive integers and add a suitably chosen phi in such a way that, again, I get a generalized wavelet system. So I get something that fulfills the Calderon condition. I get an inhomogeneous system. Okay, all of these systems are special cases of the wavelet systems that we want to study. Okay, and what do we want to study? As I said, we want to study approximation theory, theoretic properties. Before we go into that, let's quickly look at possible interpretation of all of these systems. So the way to think of it is obviously by the convolution theorem. So this circle here should not be composition, but actually pointwise multiplication. We all know convolution becomes multiplication in Fourier domain. So essentially what you can think of the psi j of being concentrated in different areas in frequency. And essentially what you do if you decompose f like that, you decompose f into different components that correspond to different areas in frequency domain. Okay, so, and what do we want to do with that? We want to study approximation properties of these systems. This uses a notion that goes back to Feichtinger and Gröbner and has been modified and somewhat sharpened in recent years by Nielsen and then Vogtländer. And it's essentially the difference is that now we switch from the wavelets as the prime object of interest to the Fourier supports of the wavelet. So we start out by a suitable collection of open and relatively compact sets that cover the frequency domain, or at least up to a set of measure 0. And we assume that we have a generalized wavelet system. So this should actually be GWS, a generalized wavelet system with a property that the wavelet Cj with little j in the index set, indexing both the wavelet system and the covering, is contained in the Fourier domain set Pj. So we have essentially, and so what you can think of is essentially you have something like a partition of unity that's subordinate to a fixed covering of the frequency domain. And then you define norms essentially by doing the following. So we read the right-hand side of this norm from the inside out. You start out with the convolution product f with pj that takes the contribution of the frequencies in the set pj to f. You measure that in LP, then you weight that with a suitable weight function, and this should be actually an LQ norm. You take the LQ norm of the whole set, of weighted norms that you have here. And so here we stick to PQ less than infinity, and then we can, for simplicity and to avoid functional analytic problems, we take the completion of that space of L2 with that norm to denote the so-called decomposition space. Okay, and the point of this is that if you impose sufficient conditions on the wavelet system C, you can essentially forget about the influence of the wavelet system C. So if you switch between two wavelet systems from the same class, it's guaranteed that you get equivalent norms and the same spaces. So the frequency covering determines the properties of the spaces. If you assume sufficiently nice coverings, and I'm not going into the details of what that means, so my whole talk is going to be about so-called structured admissible coverings without mentioning the term from now on. So essentially the idea is you start from a covering, then you take a partition of unity, or rather a squared partition of unity in frequency domain that's subordinate to that, and you define a scale of spaces. And the scale of spaces essentially allows you to quantify Fourier domain decay. So again, from the inside, reading the formula from the inside out, you start out with the LP norm of the convolution product. That's the contribution of Pj to F. You measure that in the P norm, and then so you then take those LP norms and measure that in a weighted LQ norm, and it allows you to say something on how fast the frequency contributions go to zero, or how fast the frequency contributions associated to different to the different areas in frequency to F actually decay with respect to norm. And you can really use that to quantify smoothness. So, for example, L2 Sobolev spaces, if you stick to that fairly easy setting, these can have a fairly simple description in terms of these spaces in higher dimensions. The game you can play, and we'll see some examples of that. You can use directional oriented systems of sets covering the frequencies to speak about directional smoothness. Okay, so here are a couple of examples that I want to quickly show. Those are all examples from the literature. Those are all spaces that were initially not, or at least most of them were not defined as decomposition spaces, but they all have a decomposition space description. As Hans Feichtinger pointed out in his talk, the modulation spaces are, so these are associated to the Gabor systems. These were kind of motivated by the homogeneous Bezov spaces, but they are different spaces, as we'll see in a minute. And then we have the anisotropic wavelet system that will give rise to the homogeneous anisotropic Bezov spaces, which was studied by, for example, Marcin Bovnik in great generality and his co-workers. If you put in the shearlet system, you shear shearlet co-orbit spaces, and there are other classes that I haven't mentioned here that have a description as decomposition spaces, and with the exception of the alpha modulation spaces, maybe these spaces were all designed with initially at least, with some other notions of, in some other way, not in a decomposition space way, but you can always realize these as decomposition spaces. And generalized wavelet query spaces, I will get back to these at the end of my talk. Okay, and here are coverings related to that. So if you remember the isotropic, if you remember the oriented wavelet system from the beginning of the talk, the corresponding wavelet covering is this. So you cut the frequency domain into annuli, and you cut each annulus into the same number of sectors. And regardless of the number of sectors, what you get in the end, according as spaces which correspond to this frequency covering are the isotropic Bezoff spaces. If you take an anisotropic, if you look at an anisotropic wavelet system, then what you get is essentially ellipsoids that change rotation and also the degree of anisotropy as the index j goes to -infinity or +infinity. That's the so-called shielded covering. So that's essentially you cut the frequency minus the middle axis into wedge-shaped sets. That's the so-called cone-adapted shielded covering. That here you cut the frequency domain into annuli with respect to the L-infinity norm, and also cut the annuli into different sectors, but the number of sectors actually increases as the scale in frequency domain goes to infinity. That's the curvelet covering. It looks kind of similar to the previous one. Again, you have as the frequencies go to infinity, you have so you have again annuli of scale 2 to the j, and you have roughly you cut those annuli into an increasingly number of wedges. Okay, all of these coverings have been used in this context, and they correspond to systems of generalized wavelet systems that have been used. Okay, and now the prize question is it possible to say the following? Is it possible so if the covering essentially determines the decomposition spaces, is it possible to just look at the covering and make statements about the decomposition spaces that arise from that? And what we want to focus on is classification. So we can say that two coverings are equivalent if the decomposition spaces actually coincide, and or if there's a canonical isomorphism between those. The question is that can one look at just the coverings and decide that without going into the details of defining the decomposition spaces? And also one interesting question that I will only mention briefly at the end is it possible to, for example, compare decomposition spaces to classical smoothness spaces, talk about embeddings, stuff like that? Okay, so we will focus mostly on equivalence, and we will try to understand, we essentially want to talk about classification. And the key to classification is essentially contained already in the paper by Feichting and Gröbner. That's a game you can always play. If you have a covering of a set, you can always use the covering to define a metric, essentially by just saying, okay, if I have 2 points in the set that is being covered, I'm just taking the minimal chain that I obtained by connecting the two with essentially neighboring sets. So what I'm looking for is I'm looking for a chain of points connecting these 2 points in such a way that each consecutive pair is contained in a common set in the covering. That defines a metric, and Feichting and Gröbner also already observed that there is some connection between the metric and equivalence of this or equality of the spaces. But the full say the full extent was realized only later, and it's mostly thanks to Felix Vogtländer and to Rene Koch. I think that the full extent was exhibited. This is the theorem. So essentially, you assume that you have two coverings, both consist of open and connected sets that can cover the same frequency set O. You have each one of these guys induces a metric on O, And then the coverings are equivalent, meaning that the underlying spaces are the same, if and only if the two metrics are quasi equivalent, which means they are equivalent at large scales, or put differently, if the identity operator is a quasi-isometry between the two different induced metrics. And by quasi-isometry, for those who don't know, essentially means you have the usual equivalence between metrics that you like and know from topology and from functional analysis, but you also allow essentially additive constants to both sides of the inequality that is boiled down to saying that the equivalence that you know and use a lot in which is without these additive constants holds for large distances. So in one way of thinking of this is that two metrics are quasi-isometric if these metric spaces look the same if you look from very far away, or at large scales only. Okay, and essentially we want to apply this this criterion now, because this is essentially what we set out, what we wanted to have. We were looking for something that, just given P and Q, lets us decide whether P and Q give the same scale of spaces, essentially have the same approximation theory. And the answer here is, well, you know, just whether that's the only thing you need to do is compute the two metrics and compare them. Okay, is that actually useful? I want to essentially present two examples. The quick one is this one. It's the curvelets versus the shielded smoothness spaces. So the curvelet space, the curvelet smoothness space corresponds essentially to is a decomposition space with respect to this covering. And what you do here is, again, you cut the frequencies into annuli of order 2 to the j, and you cut each annulus, every second annulus every annulus you cut into sectors of diameter 2 to the j over 2. So essentially every second annulus you double the number of directions. And for the shearlet covering, you essentially play the same game, except you don't use the Euclidean norm, you use the L-infinity norm. And there's a paper by Labate and co-authors where they very meticulously prove that these spaces coincide. And it turns out that, I mean, at least right now it looks like something that you can decide by looking at the pictures. And it's essentially, you could say, a simple exercise. You can actually go about computing the metrics, or what's more clever here is to compute a metric for which it is easy to prove that it's quasi-equivalent to both of those. But in any case, this is just an example way where it becomes the whole problem becomes kind of visual. I think for many people who work in this area, it wasn't really a big surprise to that Labate and his co-authors showed this result, but because the intuition was always there. But the whole point of the theorem that I showed, the whole point of looking at this from the metric viewpoint is that the intuition can now be put in a very succinct form. It's just about comparing metrics. And then the problem doesn't necessarily become easier. Comparing metrics can be a tricky problem in itself, but it's only about metrics after all. You don't have to know anything about Fourier analysis at this stage. Okay, this is the one example I want to show. The second one is a class of examples, and it takes a bit longer to explain. So here I want to talk about shearlet dilation groups. So there were two general classes in arbitrary dimensions that were considered. So below the diagonal, in both cases, you only have zeros. Then on the diagonal, you have, in the one case, you had powers of a single parameter A. And then above, only in the so-called original shearlet dilation groups, you only had arbitrary entries in the first line and zeros below. and then Dahlke, Teschke, and Heuser came up with a second family of groups where you essentially replaced this single line by a triplets type structure, and here you just allowed they just allowed a to the power 1 on the diagonal. And the basic question that arose there was, so these are groups that define wavelet systems in a certain sense. I'll talk about that in a second. And you can define function spaces in terms of decay, which are very much like decomposition spaces. And the prize question was, do they have the same approximation theory, which means do they have the same coorbit spaces in that setting? And okay, so the question was easy to pose, but back when the groups were designed, there wasn't really a handy criterion. I mean, everyone probably guessed that the coorbit spaces were different, but there was no criteria. Okay, but now we have a criterion, we can see how this works. And we want to put it to work on a larger class in some sense. So I want to talk about general Schiller dilation groups. Those are groups that are made up of the two ingredients we have here. So what we have here is essentially, so each group element here, but also here, you can also factor essentially into the diagonal part and into the unipotent part. So here I've written it as one matrix, but you can also factor it as the diagonal part times a slightly different part above the diagonal, and here the same. So here you have a to the power a, and then you can multiply. You can write this as the diagonal part times a second unipotent matrix that is essentially, I think, the second matrix divided by something like this. So and the general dilation, Schiller dilation groups that we want to study are those that are essentially made up of those two parts. So S corresponds to the unipotent part. It's a closed abelian matrix group. So abelian was also, so the unipotent parts were also abelian, consisting of upper triangular matrices with one on the diagonal. So unipotent group and a one parameter group of diagonal matrices in such a way that each element in the full group can be written as a product of those two. So it turns out that it's then a semidirect product of S, that's the normal part, and D, that's the part acting on the normal subgroup. Okay, and the question was, okay, so you can now go ahead and define something, look at the family of convolution products, and you can look at spaces that define coefficient decay with respect to this transform. And except for the fact that H is now a continuous set of dilations that act on the single function psi to define something like a generalized wavelet system, we're pretty much in the setting that we started out with. And so these co-orbit spaces, Charlie Brechnik will talk about those co-orbit spaces in a different setting tomorrow, are another way of defining spaces in terms of coefficient decay. And it can actually be shown quite easily that these spaces do have also decomposition space description. What you need is essentially to define a covering of the frequencies from the group of dilation H. And you can get that by discretizing the group, picking a suitable discrete subset of the group and letting that one act on a single open connected set. And then the question was, back to the question we would like to study, which of these groups actually have the same scale of co-orbit spaces, which becomes a question about decomposition spaces and can be answered with that. And the whole answer is encoded essentially in the way that the group acts on the frequencies. And we will not talk about all Schiller dilation groups, we will only talk about abelian such groups. And these have a particular structure. These, if you look at the Lie algebra of such a group, it turns out to be an associative algebra that of a particular type. Namely of, so you have first the diagonal part that's multiples of the identity, and then you have an upper triangular part that corresponds to a nilpotent algebra. And you can actually show that all of these Lie algebras of such an abelian Schiller dilation group are actually in one-to-one correspondence with certain associative commutative algebras that are given abstractly of the form unity plus an nilpotent group. Okay, plus an nilpotent algebra. So, and there's quite a lot of them in higher dimensions, and we want to classify them up to equivalence in terms of approximation theory. Okay, and this is the result we get. So we have two abelian shielded dilation groups, so abelian groups of the types that we discussed. Then you can show the following equivalence. H1 and H2 have the same co-orbit spaces if and only if we have the action of both spaces of both groups H1 and H2 on the frequencies, and we can use this. So this action is transitive and free on an open subset O of the frequencies, and on the same open subset. That's important. So we can essentially use this to induce a mapping from one to the other. So this doesn't necessarily respect the group action. That's just obtained by taking one quotient map going this way and taking the inverse going back. And it turns out that the groups have the same co-orbit spaces, which means the wavelet systems have the same approximation theory, if and only if this map is quasi-isometric between the groups with respect to word metrics. Or put differently, and that's another surprise, is that the only thing you need for that is that the groups are actually conjugate. So it's the case, these groups are in the same equivalence class in terms of approximation theory, if and only if they're in the same equivalence class in terms of conjugacy, which means, and that's the case if and only if the associated algebras are actually isomorphic. Okay, here's a short sketch of the group proof. So the first equivalence holds in more generality. So this whole thing about having the same co-orbit spaces, being able to check that using a particular map between the underlying dilation groups, and checking that for quasi-isometry, that holds in more generality. And also going from C to A has a fairly simple general proof. The only thing that's specific to abelian shielded dilation groups is the step from B to C. How does that go? Okay, so we go to the Lie algebra level, and we recall that we know that it's an associative matrix algebra. And what we also know is, by very basic Lie theory, the exponential map is a group isomorphism onto the connected component of each HI, and the associated map maps those connected components onto each other. So what we do is we concatenate with X and log, those are group isomorphisms, and we get a polynomial quasi-isometry. So polynomial because essentially what we're looking at is just the nilpotent part, and on the nilpotent part, log and X are actually polynomial maps. So what we do get in the end is a polynomial quasi-isometry between vector spaces, and that turns out to be just that can only be an affine map, and then we can discuss away the additive part, and we end up with a linear map. And in the end, what we get is that the group are actually isomorphic, then the algebras are isomorphic, but if the algebras are isomorphic, this is what we know from from the theory I related before, those have to be conjugate. So in the end, we have that the algebra isomorphism gives rise to conjugacy, and groups that have the same approximation theory must be conjugate under one matrix. Okay, so this was a class of examples that was supposed to show that the metric criterion can actually be used, and it can be used to describe, to determine whether two groups have the same approximation theory in a large class of settings. And just to recap, the main thing, decomposition space description of those spaces allows to is applicable to a large variety of function spaces. We can boil down classification to quasi-isometry. What I didn't talk about here, but what's done in another paper, you can play the same game with anisotropic Bezier spaces. So here you have two different anisotropic matrices, and you ask yourself, when do they have the same spaces, the same anisotropic Bezier spaces? And that can be worked out completely using the theory we used here for other purposes. Yes. this can also be applied to embeddings, also to embeddings into smoothness spaces, to embeddings into Bezos spaces and IP spaces. And I expect that the metric viewpoint will actually make these embedding results easier to understand. Okay, and that's where I'm finished. I thank you for your attention.
Thank you for your interesting talk. So please, any questions?
I would have a question about the maybe. Sorry, somebody else is.
No, please go ahead. I'll ask afterwards.
Okay. So I noticed that you used metrics which were natural, but maybe they are not the only one. And in addition, what seems to count is the behavior at infinity. Yes. So I think that a natural question would be, can you reformulate all this in terms of coarse geometry instead of a metric?
You mean in terms of coarse structures?
Yes, coarse structures and equivalence.
Probably yes. So as you may have noticed, I'm coming at this so to speak from the other end. So coarse geometry is something I'm still learning about. So that's why probably I might be missing a couple of aspects from the coarse geometry point of view that will be important in this. I, for one, I'm quite comfortable with metrics to begin with, so right now I don't see a deficit. But I'm not excluding this.
Yes.
So right now I don't really know. For me, a metric is something very easy to grasp in a sense, even though that's probably deceiving a little. So the problem, the main problem, whether there's a quasi-isometry. So first of all, I suspect that it's actually equivalent to being coarsely equivalent. So the difference between quasi-isometry and coarse equivalence here doesn't really matter, because the metrics have certain geodesic properties, right? So they are essentially, I mean, they're usually you have a geodesic between 2 points if the distance is finite.
Sure. I basically wanted to ask if the behavior of the metric space locally is important, or only
the local behavior is not important.
Yes.
That's right. It's just, I mean, it's just about behavior at infinity, if you will.
Okay, so this is, I think, the main reason of coarse geometry replacing metric spaces. And this is possible just on RD, or you can imagine this on other type of, let's say,
right now, I would have to struggle. Say in a non-commutative setting, for example, I'm not sure I would be able to come up with an educated guess how this would look like, to be honest, just because the structures are so different. So like the unitary dual, that's of a non-abelian group, to try to come up with something similar there. I don't know whether anyone has thought about this, but I find it hard to speculate.
Okay, but in another direction, maybe without relying on symmetry, manifold replacing RD would be possible. So
I guess my guess that's in principle that's an interesting question. I think the main obstacle there is to understand when being in such a space, in a decomposition space, is actually a local property. So the game that you're playing on manifolds is cutting, right? You're cutting your manifold into pieces, and locally you're measuring in some space, and then you're somehow then you take something like the sum of the component pieces. And I know that for some smoothness spaces this works fine, but not for all of them. And I think that would be an interesting project to understand which coverings work and which don't. My guess is that it depends on the type of coverings for which this works.
Okay, thank you very much.
Thank you.
So any other questions?
I will withdraw mine. I'll ask privately, since I think it's soon time for the next speaker.
Okay. Thank you, Professor Führ, for an interesting talk. So now we move on our last talk. I'm pleased to announce Professor Jeremy Tyson.
Hello, can you hear me?
Yes.
Yes, all right. Let me share my screen.
Yeah.